Out here, in the soft edges of night, it's just you and a quiet sky, with planets and moons turning somewhere far beyond the rooftops and clouds. Most of the stories we hear are about the big, bright worlds, the giants that steal the spotlight. But tonight, I'd like to sit with you in the hush and turn our attention to the tiniest places that circle our Sunday. Little frozen spheres, dusky rocks, and hidden moons small enough to overlook, yet holding secrets large enough to change how we see everything. We'll wander slowly among them, like moving through a small museum after closing time, letting each faint light and forgotten object tell its story. No rush, no pressure, just a gentle curiosity and the feeling of being trusted with something quiet and true. If these late-night journeys into space help you unwind or make the universe feel a little closer, a soft like and a quiet subscribe are always appreciated, only if it feels right. Tonight, the small worlds are waiting. Out among those small worlds, one of the first to step out of the darkness for us was Vesta, and the year was 2011. For more than 2 centuries, Vesta and its neighbors had been little more than bright pinpricks in a telescope's field of view, tiny wandering stars with names and numbers but no real faces. Astronomers could track their paths and guess at their sizes, but in the end all they had were specks on glass plates and dots shifting against the starry background. At the beginning of the 19th century, when the sky was being charted with new patience and new instruments, the first of these objects was spotted, Ceres, in 1801, welcomed as a brand new planet hiding in the wide gap between Mars and Jupiter. Soon after came Pallas, then Juno, then Vesta. For a while, the solar system seemed to be filling with small planets, as though nature had tucked a whole family of them into that quiet lane between the reddish world of Mars and the realm of the giants. If you could step back into the year 1845 and sit beside an astronomer of that time, their map of the solar system would look a little different from the one in your mind. Neptune was not yet on the page. Instead, they would quietly list 11 planets, the familiar 7 from Mercury out to Uranus, and then 4 tiny newcomers, Ceres, Pallas, Juno, and Vesta, sharing a wide ring of space. But telescopes kept improving, and the sky did not stop at 4. More of these small bodies appeared, then dozens, then hundreds, and eventually a vast population. What had seemed like a handful of little planets turned out to be fragments and leftovers scattered across a broad belt. Astronomers realized that they could not sensibly call every one of these objects a planet. The categories shifted, and those 4 early finds lost their planetary status and settled into a different role as the original large asteroids of the main belt, just 4 among millions. Even with that new label, they remained special. They were big enough to have history written into their interiors, old enough to remember the solar system's childhood. And yet, right up until the second decade of the 21st century, no spacecraft had ever flown close enough to reveal their true shapes and scars. We had walked on the moon, orbited Mars and Jupiter and Saturn, and sent probes to the outskirts of the planetary system. But those first 4 asteroids still hovered in our imagination as unresolved dots. For Vesta and for Ceres, that quiet ended when a small, patient spacecraft called Dawn arrived. Dawn left Earth in 2007, its sides bearing wide solar panels like folded wings. Its destination was not a single world, but 2. First, Vesta, then Ceres. To fall toward one target and stay is familiar. To fall toward one, settle into orbit, leave again, and then be captured by another is something else entirely. For that, Dawn needed a different kind of engine. Instead of relying on short, fierce blasts of chemical rockets, Dawn carried an ion thruster, a drive that hums rather than roars. Inside it, xenon gas was ionized, and the charged atoms were flung out the back by electric fields at extraordinary speeds, roughly 150,000 kilometers an hour. Each ion leaving the spacecraft gave it a tiny nudge in the opposite direction. The push was so gentle that, if Dawn were sitting still, it would take days to reach the sort of speed you might feel in a slow car. But in the emptiness of space, that whisper of thrust could be applied almost all the time. Day after day, the engine glowed, using only a modest amount of xenon to slowly bend the spacecraft's path and change its speed by nearly 2 kilometers per second. To help it reach Vesta, Dawn also borrowed a little momentum from Mars, looping past the red planet and letting its gravity twist the trajectory. On board, the quiet engine kept shining, and the spacecraft slid patiently toward the region where the asteroid belt begins. Every hour of that steady push was a small promise that the blurred point of light named Vesta would one day grow into a world filling the camera's fields of view. In July of 2011, after 4 years of this gentle persistence, dawn finally arrived. The gravity of Vesta, weak but real, reached out and caught the spacecraft, and the ion engine was used to shape its descent into orbit instead of slamming on any kind of cosmic brakes. As dawn spiraled downward into closer and closer paths, the images it sent home began to resolve. The science teams had expected something roughly like a battered, rounded rock, irregular, cratered, but familiar. Instead, what unfolded on their screens had its own strange elegance. Vesta's form is not quite that of a simple ball. At first glance, it looks a little like a sphere that someone has pressed down at one end, squashing it gently out of shape. Part of this is simply that Vesta is not very large. With a diameter of around 500 kilometers, it is far smaller than a true planet or even our moon. Its surface area is comparable to that of a mid-sized country on Earth, something you can almost imagine walking across rather than an endless globe. At that scale, its own gravity is not quite strong enough to pull everything into a perfectly smooth, rounded shape. But size is only part of the story. The more striking reason for Vesta's odd silhouette lies in its past. Long ago, more than 1 billion years in the past, when life on Earth was still microscopic, Vesta was struck not by one, but by 2 enormous impactors, each large enough to count as a small world in its own right. Both blows landed near the South Pole. They did not just dent the surface, they carved deep basins that cut down through the crust and reached toward the mantle beneath. Over time, the hot material that had been disturbed cooled and hardened, and what remained was a colossal, overlapping scar system. The younger and better preserved of these scars is known as Resilvia. In images from dawn, it appears as a vast, circular depression dominating the southern hemisphere, with its edges and structures rippling outward. Around its rim, the walls do not simply drop in a neat curve. They step and slump in terraces, forming troughs and valleys that loop around much of the asteroid. At the heart of Resilvia stands a central peak, a mountain built when the crust rebounded upward after the violence of the impact. For a while, before better measurements came in, this peak was thought to be the tallest known mountain in the solar system. Later, more precise data returned the record to Olympus Mons on Mars, but Resilvia's central summit remains immense, tens of kilometers high, rising in a single broad swell from the basin floor. On a world only a few hundred kilometers across, such a feature looks almost exaggerated, like a blister swelling near the South Pole, plainly visible even from high orbit. Those ancient impacts did more than reshape Vesta itself. When the projectiles slammed into the asteroid, they launched vast amounts of rock into space. So much material was excavated and flung away that fragments of Vesta can be found scattered throughout the asteroid belt and beyond it as well. Astronomers have identified a family of asteroids that share Vesta's distinctive spectral fingerprint, the way they reflect sunlight across different colors, and grouped them together as V-type asteroids. Many of these small bodies can be traced back, through their orbits and compositions, to the great southern basins on Vesta. Some of the debris traveled even farther, taking long, slow paths through the solar system until gravity nudged them onto crossing orbits with Earth. When those pieces finally fell through our atmosphere as meteorites, some survived the fiery plunge and landed on the ground as stones. Today, about 1 in 20 meteorites found on Earth is believed to have come from Vesta. They carry the name HED meteorites, short for Howardites, Eucrits, and Diogenites, 3 related rock types that, together, tell the story of a world that once had a molten interior and a layered structure. This has given planetary scientists an unusual gift. Without having to mount a sample return mission, they have been able to hold pieces of Vesta in their hands, to polish thin slices of its crust and mantle, and look through them under microscopes. The textures and minerals in these rocks, combined with Dawn's maps of Vesta's surface and gravity, reveal that Vesta is something rare, the last surviving rocky protoplanet in the inner solar system. A planetary embryo that never quite had the chance to grow up. In the earliest days of the solar system, long before there were full-sized planets, the space around the young sun was filled with dust and ice grains swirling in a disk. Small clumps stuck together, then collided and merged into larger bodies called planetesimals. Those, in turn, crashed and combined into still larger objects, protoplanets, each a rough draft of a world. Over millions of years, most of these early bodies either merged into the planets we know today or were shattered and ground down into rubble. Vesta is one of those survivors. It bears the marks of early heating and differentiation. At one time, its interior was hot enough for heavier elements to sink inward and lighter materials to float upward, creating a layered structure with a dense metallic core, a rocky mantle, and a crust on top. Dawn's measurements suggest that Vesta's iron-rich core is a couple of 100 kilometers across, small by planetary standards, but enormous when you imagine that scale inside so small a world. But unlike those larger siblings, Vesta's energy did not last. Over time, it cooled. The mantle solidified, volcanic activity faded, and the interior stiffened. By the time those great impacts struck near its south pole roughly 1 billion years ago, Vesta was no longer warm and flexible enough for its shape to relax back into a neat, rounded form. The blows carved away a huge chunk of its southern hemisphere, and the asteroid was left permanently misshapen, pulled by its gravity toward roundness but frozen in an in-between shape. If those collisions had never happened, and if Vesta had had just a little more mass, it might well have met the modern definition of a dwarf planet, a body large enough for its own gravity to mold it into a nearly spherical shape, but not dominant enough to clear its orbit of other debris. Instead, because both its size and its late injuries work against that roundness, Vesta sits just on the near side of that threshold. As for why Vesta stayed small, astronomers often look to the giant, sitting just beyond the asteroid belt, Jupiter. When Jupiter formed, its immense gravity stirred and disturbed the region between it and Mars. Material that might have gathered into one or two additional planets was instead jostled, scattered, and repeatedly smashed. Growing worlds were pulled off balance, their orbits stretched and twisted. In that restless environment, Vesta began to form, accreting material and heating up inside. But Jupiter's presence likely stole away much of the mass that could have fed its growth, or kept the region so excited that Vesta never had a calm chance to become larger. And so Vesta remained what it is, a half-finished world, with a heart like a small planet's and a body scarred and chipped by deep time. When Dawn slipped into orbit, that history finally came into focus. The squashed outline, the immense southern basin with its central peak, the network of troughs and ridges wrapping around its waist. A moving speck of light became a real place you can picture circling slowly above, a relic that still remembers the era when planets were being assembled, grain by grain, collision by collision. In ordinary light, though, Vesta hides that drama behind a quiet face. If you could float nearby and look with your own eyes, you'd mostly see a shaded world in soft grays and browns, a slightly lopsided sphere that seems calm and unassuming, like a worn stone in a riverbed, until you begin to notice how that stone is dented, carved, and folded by everything it has survived. Dawn's cameras, though, could see in many wavelengths. When scientists combined those views into false color maps, subtle differences in the minerals at the surface turned into patches of deep blacks and warm reds that don't match any natural color you'd see, but reveal the hidden variety in Vesta's crust. Some regions appear as dark, almost soot-black smears. These are thought to be material brought in by ancient impacts, foreign dust and rock flung across the landscape and mixed into Vesta's own surface. Other areas glow in reddish tones, likely places where rock was once melted during powerful collisions and then cooled again. The false colors act like a translator, turning slight chemical differences into something our eyes can follow, and what once looked bland becomes a tapestry of different histories laid together. Dawn also found shapes that seem to whisper of movement, even though Vesta is considered extremely dry. Its crust is thought to contain very little in the way of volatile materials like water ice. On paper, it is a hard, airless world with no liquids flowing anywhere. Yet in one small crater, only a few kilometers wide, Dawn saw a narrow channel running downslope from the rim, like a frozen streambed. In false color, the material inside that channel stands out as different from the surrounding terrain, hinting that something once flowed or slid there. The exact origin of this feature isn't fully settled. One idea is that the impactor that carved the crater brought in material that melts more easily, or contained its own ices and volatiles. The energy of the collision could have briefly turned that material into a slurry that moved downslope before freezing and locking into place. Whatever the details, it is a reminder that even dry bodies can experience short-lived, complex behavior when something strikes them hard enough. Another surprise came from a fresh crater named Marcia. Near its floor, Dawn's images revealed pitted terrain, a field of small, irregular pits clustered together, as if the ground had been peppered by tiny, shallow explosions. Before Vesta, this kind of terrain had only been seen on Mars, a much larger world where subsurface ice and past water activity are already part of the story. To find similar textures on a small, supposedly parched asteroid raised a quiet question. What was happening inside those rocks? The leading explanation involves hydrated minerals, rocks that carry small amounts of water locked into their crystal structure. If such minerals are suddenly heated, for example by the intense energy of an impact nearby, the trapped water can flash into vapor. On Vesta, that vapor bursts outward into space, tearing tiny pieces of material away and leaving little pits behind. Many such micro-explosions over a region can create the pitted terrain that Dawn saw. If this picture is right, then Marcia's pits reveal that parts of Vesta's crust once interacted with water, even if only in trace amounts. The asteroid may not have lakes or oceans, but it carries minerals that remember contact with water in some earlier phase of its history. That memory stayed hidden until a new impact woke it up and let it escape in a series of tiny sighs into the dark. Marcia is also one of 3 overlapping craters that together resemble a snowman. 3 circles, large, medium, and small, stacked roughly in a line. The nickname is lighthearted, but the terrain around this snowman is scientifically telling. Compared with rougher regions nearby, the area looks relatively smooth, as if someone has laid a blanket over older features. The current understanding is that when the impacts happened, they blasted out huge amounts of pulverized rock. Much of that ejecta fell back, coating the surroundings in a thick layer that softened sharp edges and filled in smaller holes. Over time, that blanket settled, leaving a landscape that looks calmer than its violent origins would suggest. After about a year in orbit, Dawn's time at Vesta drew to a close. The spacecraft had traced careful paths at different heights, mapped the surface, and measured subtle changes in gravity that spoke of Vesta's layered interior. When it was time to depart, there was no single dramatic push, just the quiet glow of the ion engine turning on again. Slowly, Dawn climbed away from Vesta's gravity. Day by day, its steady thrust nudged its orbit outward. Eventually, the asteroid's pull loosened enough that Dawn slipped free and began to fall toward its next destination. Ceres, the largest object in the asteroid belt and the only dwarf planet there. The journey from Vesta to Ceres took about 2 years. During that time, the spacecraft continued its patient work, monitoring its systems, rationing its remaining xenon, and adjusting its course with long, faint burns. On Earth, scientists and engineers watched each update, feeling a quiet mix of routine and anticipation. Vesta had revealed a rocky embryo. Now the mission was sailing toward a world that seemed, on paper, very different. Even with the sharp gaze of the Hubble Space Telescope, Ceres had never been seen clearly. It appeared as a fuzzy disk with hints of light and dark, but no real detail, no craters you could trace, no mountains you could outline. Its size and mass were known, and its overall density suggested it must contain a lot of water or ice mixed with rock. Beyond that, Ceres was mostly a blurred outline and a few numbers. As dawn approached, the blur began to sharpen. Images that once showed only a featureless patch of gray started to reveal bowls and rims, bright splotches, and darker planes. Craters popped into view, then multiplied, until it was clear that Ceres, like Vesta, had been hit again and again. But it did not look exactly like a scaled-up asteroid. There were fewer, large, sharp-edged craters than expected, and some regions seemed softened or smoothed, as if the surface had changed after some of those impacts. And then there were the bright spots. At first, they were tiny, dazzling dots, standing out against the muted background so bright that they sometimes overexposed parts of the images. The most striking ones lay inside a medium-sized crater. From far away, it looked like a single bright patch. As dawn drew closer, that patch resolved into 2 points. Closer still, and those 2 points became a cluster of distinct spots scattered across the crater floor and central region. People following the mission were fascinated. The spots seemed too bright to be ordinary rock. Some thought of exposed ice. Others suspected salts or other reflective minerals. For a while, speculation flowed, but the spacecraft kept doing its job, gathering more data, measuring spectra, and watching how light bounced off those regions at different angles and wavelengths. To understand the bright spots, it helps to consider what kind of world Ceres is. Unlike most of its rocky neighbors, Ceres seems to be an icy body in disguise. Its outermost layer, the part we see, is dusty and rocky, a fragile crust shaped by countless impacts. But that crust is porous, with empty spaces between grains and fractures that allow water and salts to sit in the gaps. Roughly speaking, you can imagine about 9 parts rock to 1 part water in the upper layers. Though that water may be frozen or locked in minerals rather than sitting as liquid. Beneath this crust, many models suggest a mantle that is more like thick, salty mud than solid stone, a mixture of ice, brine, and rocky fragments that can slowly shift and flow over long timescales. Deeper still, there may be a core rich in hydrated minerals, where water is bound into the structure of the rock. The exact layout is still uncertain, but most pictures of Ceres's interior agree on one thing. There is a great deal of water there, perhaps nearly half of the dwarf planet's total volume when all forms are counted. On a world like this, ordinary ice near the surface is not stable when it is directly exposed. In the vacuum of space, under unfiltered sunlight, water ice sublimates, skipping the liquid phase and turning straight into vapor. Over time, exposed ice disappears, leaving behind a dustier residue. That is why the surface looks rocky, even though Ceres is so water-rich inside. The uppermost layer is like a crust that hides a colder, wetter interior. The bright spots, now known to be clusters of salt deposits, seem to be places where that hidden interior has briefly reached outward. On Earth, when we think of volcanoes, we picture blazing lava. On Ceres, the equivalent process is much gentler and colder. Instead of molten rock, the lava is briny water, a mixture that can stay liquid at lower temperatures than pure water. When such brine rises through cracks or weak zones and reaches the near surface, it can collect in shallow pockets or seep out onto the floor of a crater. There, in contact with vacuum and sunlight, the water component quickly sublimates away. The dissolved salts stay behind. As they crystallize, they form bright, reflective patches that stand out strongly against the darker, older terrain. The largest and most famous of these deposits lies inside a crater named Akator. Using Dawn's data, scientists built 3-dimensional models of its interior. They found a central dome and surrounding bright streaks and patches, as if something from below had gently lifted the surface and then leaked outward. Instruments also detected faint, temporary hazes above this region at certain times, suggesting that water vapor was occasionally present there, hovering briefly before dispersing. It was a soft hint that, even now, Ceres may be venting tiny amounts of gas from its depths. Over time, the salt-rich areas on Ceres slowly darken as they're bombarded by micrometeorites and bathed in radiation from the sunday. The brightest patches we see today are probably the youngest, the freshest traces of buried brines that have recently reached the surface. Older cryovolcanic sites are likely scattered all across the dwarf planet, but their once vivid deposits have faded back into the surrounding gray, leaving only subtle hints of where they once gleamed. Those brilliant patches aren't confined to a single famous crater. As Dawn's instruments kept working and the maps grew sharper, many smaller bright regions emerged scattered across Ceres like faint embers on a dark hearth. Some stand out as crisp, concentrated spots. Others are softer and more washed out, as if they've been sitting there quietly for a long time. Together, they suggest that salty water has found its way upward in many places and at many different moments in Ceres' history. In this way, Ceres reveals itself as a world that, while outwardly calm, is not completely frozen in time. Its porous crust, its hidden mixtures of rock, ice, and brine, and its slowly renewing surface tell a story of gentle, long-lived activity. Where Vesta shows us a rocky embryo that never grew into a full planet, Ceres shows us an icy body that kept much of its water and continues to reshape its face with subtle outbursts of salt and light. Under Dawn's patient watch, the two of them offer different, softly spoken ways that small worlds can hold on to the secrets of the early solar system and share them little by little. Water itself was also found in subtler ways. Ceres doesn't have lakes shining under a blue sky, but traces of water and ice appear in its spectra and in the behavior of its surface. One of the quietest, most intriguing hiding places lies near the poles. Because Ceres's axis is only tipped by about 4 degrees, sunlight falls almost straight down on its equatorial regions and barely brushes the deep bowls near the poles. In some polar craters, the rims are high enough that the sun never quite climbs over the edge. Their floors sit in permanent shadow, locked in a darkness that has lasted for millions, perhaps billions, of years. In those cold traps, temperatures are low enough that exposed water ice can endure without quickly turning to vapor. The ice is protected not by an atmosphere or a thick blanket of rock, but simply by the absence of light. Dawn's instruments detected signatures of this buried frost, showing that Ceres, like our own moon, keeps pockets of ancient ice tucked away at the bottoms of craters that never see dawn. It is a gentle arrangement. The sun brightens the rims and upper walls, but the depths remain in a kind of eternal twilight, quietly preserving what would vanish elsewhere. Everywhere Dawn looked, the surface of Ceres bore marks of impact. Some craters are clean and round, their rims sharply defined, as though stamped into the ground by a single clear blow. Others are more chaotic floors, marked by ridges, scars, and slumps, places where material has shifted after the initial impact. Many are complex craters, not just simple bowls, but structures with peaks rising in their centers, formed when the surface recoiled upward after being compressed by the strike. There are also hints that crater walls do not always hold their shape. In some images, slabs of material seem to have detached and slid inward, leaving gaps in the rim and hummocky debris below. One striking example shows a large block that appears to have broken free and moved downslope, like part of a cliff that finally gave way under its own weight. Smaller rocks have tumbled too, leaving long, thin streaks behind them on the crater walls, silent trails written in dust and loose grains. Some of the most evocative views Dawn sent back were taken at a slant, skimming along the limb of the dwarf planet. In those oblique images, craters overlap and cast shadows across one another. Rims stand like low, broken horizons, and gentle slopes fade into the distance. Without clouds or haze to soften the view, every edge is crisp. Yet, paradoxically, it can be hard to tell what is small and close or large and far away. Our eyes are used to atmosphere and familiar landmarks to judge distance, and on Ceres there is nothing but sharp light, dark shadow, and the patient curve of the surface. Threaded through this landscape are fractures, long, narrow lines where the crust has been pulled or squeezed. Some appear as grooves and troughs, shallow valleys that run for many kilometers. These are thought to form where the crust has been stretched, opening subtle gaps that later slump and widen. Other fractures show up as chains of low hills or ridges, places where the surface has been compressed instead, wrinkling it into rows of modest mountains. Not all of these features are ancient. Some fracture systems are relatively young in geological terms, perhaps only a few 100 million years old. On Ceres, where time is measured in billions of years, that counts as recent. The youth of these grooves and ridges hints that the crust has remained mechanically active over long spans, slowly adjusting, cracking, and shifting as buried ice creeps, brines, move, or the dwarf planet responds to the stress of impacts and internal cooling. Among all these structures, one stands out almost theatrically: Ahuna Mons. Rising from otherwise unremarkable terrain, this lonely mountain is about 20 kilometers wide and roughly 5 kilometers high. It does not sit at the center of a large impact crater, nor does it lie along a clear ridge system. Instead, it towers almost by itself, a broad dome with flanks streaked by landslides, as if its slopes have been slowly shedding material in thin avalanches. Ahuna Mons is puzzling precisely because it is unique. If there were many such domes, scientists might say that Ceres undergoes some global process that builds them. Instead, Ahuna stands alone, like a single frozen swell on a quiet sea. The leading idea is that it is a cryovolcanic dome, a volcano not of molten rock, but of icy, salty material that once rose from the interior. Over time, that cryomagma would have thickened and hardened, leaving behind a mountain of refrozen slurry and debris. One possible trigger for its formation involves a concept called the antipode. When a large impact strikes a world, the shock waves spread through its interior. On the opposite side, the antipodal point, those waves can sometimes converge and concentrate. In several places in the solar system, such as Mercury, the region directly opposite a major impact basin shows oddly disrupted terrain, as if the crust there has been shaken and fractured from below. Ahuna Mons may sit near such an antipodal focus. If a big impact on one side of Ceres sent seismic energy racing through the interior, the waves could have met and interfered on the far side, weakening the crust there. In a body whose subsurface contains brine and ductile ice, that disturbance could open a path for material to rise. The result might be a localized cryovolcano, building itself quietly over long periods until it reached the dimensions we see today. In shape, Ahuna Mons has some kinship with dome volcanoes. Elsewhere in the solar system, slowly built structures formed by thick, sticky material that piles up rather than spreading out easily. On Earth, Mount Street Helens has grown domes in parts of its history. On Mars, certain rounded volcanic constructs may have formed from similarly viscous lavas. On Ceres, the material would have been colder and saltier, but the basic idea is the same. Something from deeper inside has pushed upward and stayed. By the time these mysteries were being teased out, Dawn had been working in space for more than a decade. It had left Earth in 2007, reached Vesta in 2011, then departed and arrived at Ceres in 2015. All that time, its ion engine had gently changed its speed and orbits, while its reaction wheels and propellant kept it pointed with the precision needed to send back exquisitely detailed data. Eventually, though, its small supply of hydrazine, the fuel used for fine attitude control, began to dwindle. In 2018, the moment finally came when Dawn no longer had enough propellant to reliably turn and keep its antenna locked on Earth. Without that ability, it could not communicate or adjust its orientation, and its active life quietly ended. Rather than letting it crash onto Ceres and risk contaminating a world that might hold delicate chemical clues, mission planners had already shaped its orbit into a stable, long-lived path. There, circling high above the dwarf planet, Dawn became a silent object, a piece of human craftwork turned into a small moonlet in all but name. For at least a couple of decades, and likely far longer, that derelict spacecraft will remain in place, drifting over the same plains, craters, fractures, and bright salt patches it once studied with such care. Its instruments are cold and silent now, but the measurements they gathered are still very much alive, unpacked and reinterpreted by people on the ground. When researchers want to understand how small bodies can be both simple and intricate at once, dry and rocky in one region, icy and softly active in another, they still turn to Dawn's maps and spectra for guidance. In that sense, Dawn's journey didn't really end when its fuel ran out. It changed roles from an active explorer into a quiet witness circling above a world whose story continues to be read through the data it sent home. Its looping path around Ceres is a quiet reminder that even modest planets and asteroids can hold deep surprises, and that a patient, gentle push, one faint ion at a time, can carry a spacecraft and our understanding very far indeed. That gentle push is part of Dawn's legacy too. Its story doesn't live only in the worlds it revealed, but also in the way we travel through space now, in the soft blue glow of ion engines that follow its example. The same kind of thruster that carried Dawn from one small world to another has begun to appear on many other spacecraft, turning what was once a bold experiment into a familiar, trusted tool. Instead of roaring with fire, these engines whisper with ions, trading brute force for patience. That patience has proved so useful that many satellites now lean on it, using small, efficient thrusters to gently reshape their orbits over months and years. High above Earth, long chains of communication satellites breathe out faint streams of charged particles to stay in their proper lanes. In low orbit, space stations and large platforms use similar systems to nudge themselves against the thin drag of the upper atmosphere, holding their paths steady. Deeper out, on the road between the inner and outer planets, new probes quietly follow in Dawn's footsteps. Spacecraft headed for the inner furnace of Mercury use ion engines to spiral down toward the sun, shedding speed bit by bit instead of slamming on the brakes all at once. Missions bound for distant asteroid systems fire up their electric thrusters on long, slow arcs, saving chemical fuel for delicate maneuvers and final approaches. Each of these journeys carries a small echo of Dawn's long cruise from Vesta to Ceres, proving that slow, steady pushing can open paths that would once have been too difficult or too expensive to attempt. If you follow one of those paths in your imagination and keep going, past the orbits of the rocky worlds and the familiar gas giants, the sun slowly shrinks behind you. Mars falls away, then Jupiter with its churning storms, then Saturn with its rings like thin, glowing spokes of ice. Farther still, the pale blue disks of Uranus and Neptune glide by, and the solar system begins to feel less like a neighborhood and more like a vast countryside with only occasional distant lights. Beyond Neptune's orbit, roughly 30 times farther from the Sun than Earth, the space around you begins to change character. The Sun is still there, of course, but its light is weaker and softer, more like a bright star than an overwhelming lamp. The warmth that once baked Mercury and lit Earth's skies is now a thin drizzle of energy falling across a much colder domain. Here, stretching from about 30 to 50 times the Earth-Sun distance, lies the Kuiper Belt, a wide, thick ring of icy bodies encircling the solar system like a faint, frozen halo. This region is not dense with objects the way a movie might show it. You could travel millions of kilometers without brushing past anything at all. But scattered through this vast annulus are countless small worlds, most of them only dim points, even in powerful telescopes, preserved by the deep cold of the outer darkness. For a long time, astronomers knew of only one resident out here that anyone talked about: Pluto. Discovered in 1930, it was treated as the lone outpost of the planetary family. A tiny, distant world with an odd, tilted orbit that dipped inside Neptune's path for part of its journey. Its size, its path, and the way it moved against the background stars hinted that it might not be unique, that it could be one of many bodies sharing that distant zone, rather than a solitary exception. In the early 1950 seconds, the idea of a belt of icy objects beyond Neptune was put into words by the astronomer Gerard Kuiper and others. They imagined a reservoir of frozen leftovers from the solar system's formation, lingering just past the known planets. But for decades, the thought remained more hypothesis than reality. The objects were too small and too faint for the telescopes of the time. Pluto looked alone because our eyes, even aided by glass and mirrors, simply couldn't see its neighbors. That changed in 1992, when a new point of light was tracked far beyond Neptune. Its orbit placed it firmly in the region that had been suspected but never confirmed. This object, known by a temporary designation rather than a poetic name, was the first recognized member of what we now call the Kuiper Belt. Once that door was open, more discoveries followed. One by one, then by dozens, then by thousands, astronomers began to find other icy bodies circling in similar realms. Pluto and its large moon Charon, known for decades before that first confirmed belt object, turned out to be part of a much wider family rather than lonely wanderers. Alongside them are other dwarf planets, such as Haumea with its stretched shape and fast spin, Makemake with its distant, faint glow, and Eris, which orbits even farther out on a long, slow path. Around them swirl countless smaller objects, icy fragments, miniature worlds, and dormant comet cores, all tracing their own elongated, tilted orbits in the thin sunlight. To get a sense of where all of this sits, it helps to picture the solar system in layers. Closest to the Sun are the rocky planets Mercury, Venus, Earth, and Mars, warm enough that any ices on their surfaces are unstable in the long run. Between Mars and Jupiter lies the asteroid belt, a ring of rocky debris occupying a band from a little over 2 to a little more than 3 times the Earth's distance from the Sunday. It holds many thousands of catalogued bodies, from the large, almost round Ceres down to boulders and shards, only kilometers or even meters across. Even though this region seems full in diagrams, the asteroids are spread out through an enormous volume. The combined mass of everything in the main belt is only a small fraction of our moon's mass. It is a reminder that belt does not mean solid. It means a lightly populated region where objects share similar distances from the Sun, each one separated from the next by huge stretches of empty space. Beyond the asteroid belt, the giant planets take over. Jupiter, Saturn, Uranus, and Neptune dominate the outer solar system, their gravity sculpting the paths of smaller bodies around them. They act as both shepherds and disturbers, sometimes protecting inner regions, sometimes flinging comets and asteroids into new, wild orbits. Past Neptune, where the Kuiper Belt begins, their direct influence fades but never completely disappears. Neptune in particular still tugs on many Kuiper Belt objects, locking some of them into orbital resonances where they trace stable patterns over billions of years. Within the main swath of the Kuiper Belt, the material is mostly ices rather than bare rock. Frozen water, frozen methane, frozen ammonia, and other simple compounds that solidify easily in the cold. Mixed together, they form the bodies that drift there, worlds that never warmed enough to melt and differentiate the way larger planets did. Because they have spent most of their existence in a deep freeze, Kuiper Belt objects are like time capsules. Their surfaces may be altered by radiation and impacts, but their interiors still carry the chemistry of the early solar nebula, the cloud of gas and dust that once surrounded the newborn Sunday. There are likely hundreds of thousands of objects in this region larger than 100 kilometers across, and many more that are smaller, icy fragments we would call comets if they ever wandered inward and grew tails. Spread over the enormous volume of the Kuiper Belt, however, they are far from crowded. The average distance between two such bodies can be on the order of tens of millions of kilometers. You could be standing on one dark, frozen surface, look toward where you know another object lies, and see nothing but stars. Yet even this immense belt has an outer edge, beyond which the population thins and the orbits become stranger. Overlapping that boundary is a region known as the scattered disk. Some objects here travel on paths that carry them far beyond the main Kuiper Belt, swinging out hundreds of times farther from the Sun than Earth before looping back inward over spans of time so long that human history is a brief flicker beside them. These scattered objects bear the marks of past gravitational shoves, most likely from Neptune and the other giants that flung them onto elongated orbits, but did not quite eject them from the solar system altogether. If you could rise above the Sun and look down, the Kuiper Belt and scattered disk together would resemble a thickened ring or a fat, uneven donut encircling the planetary system. Far beyond that, extending thousands to tens of thousands of times farther than Earth's orbit, theory suggests there is yet another structure, the Oort cloud. Unlike the flattened, ring-like Kuiper Belt, the Oort cloud is thought to be roughly spherical, a vast shell of icy bodies surrounding the Sun from all directions like a distant, invisible bubble. We cannot see the Oort cloud directly. Its members are too far away and too faint. But the long-period comets that occasionally sweep through the inner solar system, taking hundreds of thousands or even millions of years to complete a single orbit, are likely visitors from that distant sphere, nudged inward by passing stars or gentle tides in the galaxy's gravity. The Kuiper Belt, in contrast, is close enough that we have been able to spot many of its inhabitants and even send a spacecraft to one of them. It is also the source region of most of the short-period comets, those that return again and again on timescales of decades or centuries. When an object from the Kuiper Belt has its orbit disrupted by Neptune's gravity, say, and begins to fall inward, it may eventually become a comet. As it approaches the Sun, its ices warm and begin to sublimate, releasing gas and dust that form a glowing coma and tail. When the comet's path carries it back outward, the activity fades, and the nucleus returns to the cold, waiting for the next inward swing. In this way, both the Kuiper Belt and the Oort cloud act as reservoirs, storing frozen bodies that can, from time to time, light up our skies. One is a thick ring just beyond Neptune. The other is a distant, almost mythic shell at the edge of the sun's influence. Together, they remind us that the solar system doesn't really end at the last planet. It fades, layer by layer, into a realm of ancient ice and slow orbits where the original building blocks of planets still drift in the dark, carrying the same simple compounds that once went into worlds, atmospheres, and somewhere living cells like ours. Every so often, one of those icy fragments is nudged just enough to fall inward. For a little while it becomes a moving star in our night sky, a soft tail unfurling behind it as sunlight wakes ices that have slept for eons. When you watch such a comet from Earth, maybe from a backyard or a window late at night, you're looking at a messenger from those distant reservoirs, a brief reminder that the cold outer regions of the solar system are not empty at all, but full of stories that occasionally drift inward, one fragile visitor at a time. Reaching those distant regions, or even just moving efficiently between the inner worlds, asks for its own kind of patience. Dawn's quiet achievement with ion propulsion left more than a trail between Vesta and Ceres. It left a sort of handbook for how to travel slowly and steadily through the solar system. Those blue glowing thrusters, once a daring test on a single spacecraft, have become part of the normal toolkit for missions close to Earth and far beyond, swapping brief, violent burns of chemical fuel for long, gentle pushes that favor endurance over spectacle. High above our planet, satellites use small ion thrusters to keep to their lanes and fine-tune their orbits, saving mass and extending lifetimes. Deeper out, probes headed for the inner flame of Mercury, or the dim light of distant asteroids, spiral along complex paths sculpted by ion engines, proving that continuous, economical thrust can open routes that once seemed impractical. Following those routes in your imagination, if you keep coasting outward past the last of the giant planets, you eventually arrive in the cold realm of the Kuiper Belt, the donut-shaped ring of icy bodies beyond Neptune. This region, which now feels like a subtle, ghostly halo around the planetary system, was not always so slight. In its youth, the Kuiper Belt is thought to have been rich and crowded, holding perhaps 7 to 10 times the mass of Earth in frozen debris. Over billions of years, as the orbits of Jupiter, Saturn, Uranus, and Neptune shifted and settled, their gravity stirred this population, flinging much of its material away. Some of those early Kuiper Belt objects were tossed inward and collided with the growing planets. Others were ejected entirely, sent drifting into interstellar space to become unbound wanderers between the stars. What remains today is only a thin remnant, no more than perhaps 1/10 of Earth's mass spread across an enormous volume. Compared with its original heft, the modern Kuiper Belt is like the faint outline of a once full ring, still there, but far less substantial than it used to be. Even now, the belt is slowly eroding. From time to time, two objects collide, not in fiery explosions, but in slow-motion crashes that nevertheless shatter and chip them. The impacts grind some material down into smaller fragments and dust. The tiniest grains, once freed, feel the sun's light and wind more strongly than its gravity, and can be pushed outward, either drifting to the fringes of the solar system or being blown out entirely. The region that once fed planets continues to shed its pieces into the dark. Gravity plays its own part in this slow rearrangement, Neptune, circling near the inner edge of the Kuiper Belt, acts like a distant shepherd and troublemaker combined. Its pull can, over long spans of time, gently reshape the orbits of icy bodies. A nudge here, a resonance there, and a once stable Kuiper Belt object can be guided onto a new, more elongated path that carries it closer to the Sunday. When that happens, the frozen, quiet body can awaken as a short-period comet. Short-period comets are those that return to the inner solar system on timescales shorter than 2 centuries. Once nudged inward, they fall toward the sun, their surfaces warming as they approach. Ices begin to sublimate, turning straight into gas and dragging dust along with them. Around the solid nucleus, a fuzzy coma forms, and twin tails, one of gas, one of dust, are drawn out by sunlight and the solar wind. From Earth, these comets appear for a time as moving smudges in the sky, then gradually shrink and fade as they swing back outward. Many familiar comets trace their origins to the Kuiper Belt or its extended scattered region. Halley's Comet, for example, follows a looping path with an average period of about 76 years. Each time it comes inward, it sheds a little more material, writing streams of dust along its orbit that later appear as meteor showers when Earth passes through them. Shoemaker Levy 9, another Kuiper Belt-born body, told a more dramatic story. Captured by Jupiter's gravity, it was torn into a string of fragments that, in 1994, plunged one after another into the giant planet's atmosphere. From Earth, astronomers watched dark scars bloom and spread across Jupiter's clouds, where each piece hit a bruise-like chain that marked the first time humans had ever seen one solar system body visibly collide with another. Jupiter, massive and resilient, absorbed the impacts without lasting harm, but the event was a vivid reminder of how objects from distant reservoirs like the Kuiper Belt can wander into the realms of the planets. Every so often, near-Earth asteroids or comets make the news when their orbits bring them unusually close to our world. One such object, an asteroid designated 2024 Y4, has been discussed because of its path through the Earth-Moon system. Careful calculations show that the chances of it striking the Moon are very small, and the odds of it hitting Earth are even smaller, tiny enough that they do not pose a meaningful threat. Likewise, the short-period comets born in the Kuiper Belt that happen to cross our orbit are tracked and monitored, and none are expected to trouble us for at least the next 100 years or more. On human timescales, these distant icy messengers are more a source of wonder than worry. Even as the Kuiper Belt slowly thins, it still represents a nearly boundless frontier of worlds waiting in the dark. Unlike the far more distant Oort cloud, which remains beyond the reach of our spacecraft for now, the Kuiper Belt has already felt the touch of a human-made visitor. Much of what we know about its population still comes from telescopes on Earth and from observatories like Hubble. But one mission has flown right through this icy realm: NASA's New Horizons. Launched in 2006, New Horizons spent nearly a decade crossing the planetary system before reaching Pluto in 2015. After racing past the dwarf planet and its moons, it continued outward into the Kuiper Belt, using its remaining fuel and careful navigation to set up a second encounter with a smaller object. That target, initially known by a string of numbers and letters, was officially named Arrokoth, meaning sky, in the language of the Powhatan people of North America. In January 2019, New Horizons swept past Arrokoth at a distance of just about 3,500 kilometers. By then, it was more than 1.5 billion kilometers beyond Pluto, making this the most distant close flyby ever achieved. Signals from the spacecraft took hours to reach Earth, carrying back images and measurements of a world that, until then, had been no more than a faint point of light. Arrokoth turned out to be small, only about 35 kilometers long, roughly 20 kilometers wide, and around 10 kilometers thick. Yet its shape was striking. Two distinct lobes gently fused together, forming something that looked like a flattened snowman. This made Arrokoth what is known as a contact binary, an object built from two once separate bodies that touched and merged but never crushed one another. At first glance, a tiny, airless lump of ice and dust might not seem like an especially important place, but the details of Arrokoth's form spoke directly to questions about how planets begin. Its surface appeared relatively smooth, lacking the deep fractures and violent distortions you might expect if the two lobes had slammed together at high speeds. Its overall structure and slow rotation hinted at a gentle history, small pieces forming nearby, drifting together in a shared cloud and gradually collapsing into the shape we see today. For decades, scientists had debated how the earliest building blocks of planets, planetesimals, came into being. One idea, called hierarchical accretion, suggested that tiny grains and pebbles collided, stuck, and grew into larger rocks, which then crashed together at increasingly high speeds, merging through repeated impacts. Another idea, often called local cloud collapse, pictured swarms of pebbles and small chunks slowly gathering under their own collective gravity. In that scenario, parts of the cloud collapse almost like a mini nebula, forming larger bodies in a relatively gentle, coordinated way. Arrokoth's quiet, undisturbed surface, its softly joined lobes, and its flattened shape all leaned toward the second story. The evidence pointed to a low-speed union, two objects that had formed side by side in the same clump of material, slowly spiraling together until they touched and stuck. There were no signs of the kind of catastrophic shattering or high-energy crashes that hierarchical accretion would naturally produce at later stages. Studies of Arrokoth's geology, internal structure, and composition, based on the New Horizons data, strengthened this picture. The more researchers looked, the more the little object seemed to embody the idea of local cloud collapse, a planetesimal born not from chaotic smashing, but from the soft convergence of nearby material. The mission's principal investigator, Alan Stern, described the conclusion as essentially settling a long-running debate. After years of modeling and argument, a small, distant contact binary had offered a clear example of how at least some planetesimals truly form. New Horizons did not only visit Arrokoth. Its primary destination, reached a few years earlier, was Pluto, a world that had lived in our imaginations for generations as a dim dot at the edge of the maps. When the spacecraft arrived in 2015 and sped past at high speed, it revealed a place far more complex than most people had expected. Orbiting with Pluto was its large moon Charon, almost half its size, along with a retinue of smaller moons, Nix, Hydra, Kerberos, and Styx, each with its own tumbling motion and reflective, icy surface. The close-up views of Pluto showed a landscape marked by mountains of water ice, dark equatorial bands, and, most famously, a bright, heart-shaped region sprawling across one hemisphere. This feature, known as Tombaugh Regio, after Pluto's discoverer, quickly became an emblem of the dwarf planet. Its western lobe, called Sputnik Planitia, is a vast plain, filled not with rock, but with nitrogen ice, a frozen sea, roughly 1,000 kilometers across and about 4 kilometers deep, making it the largest known glacier in the solar system. Sputnik Planetia's surface is patterned with polygonal cells, thought to be created by slow convection within the nitrogen ice. As slightly warmer material rises and cooler material sinks, chunks of water icebergs float within it, embedded like islands in a solidified but slowly moving sheet. To one side, the eastern lobe of the heart appears somewhat different in texture, but still bright, likely coated by nitrogen ice and other volatile ices that have migrated from the main basin and settled there as frost. The data from New Horizons suggested that Pluto may harbor more than just frozen plains and thin air. Some interpretations pointed to the possibility of a deep interior ocean of water mixed with antifreezes like ammonia, kept from freezing solid by residual heat and insulating layers above it. Such an ocean could help explain certain patterns in Pluto's shape and gravity field, and might bear on how Sputnik Planitia formed and evolved. Later studies offered another intriguing idea. Instead of being driven solely by internal ocean dynamics, Pluto's heart-shaped feature might trace back to a massive, low-velocity impact early in the dwarf planet's history. In this scenario, a large icy body struck Pluto at an oblique angle, not straight on, but more like a glancing blow. The result would have been a broad, elongated excavation in the crust, a kind of enormous splat across the surface that later filled with nitrogen, ice, and other volatile materials. To picture it, you can think of tossing a water balloon so that it skims across dry pavement. Rather than bursting in one tight circular stain, it scrapes along and bursts in motion, leaving an extended splash shaped by its path. On Pluto, the projectile would have been made of ice and rock instead of latex and water, and the surface would have been colder and harder than any pavement on Earth. But the underlying idea is similar: a slow, angled impact, spreading its energy and material across a wide area, carving the basin that became Sputnik Planitia and setting the stage for the double-lobed heart we see today. Whether that giant impact, a subsurface ocean, or some combination of both is ultimately responsible for Pluto's heart, New Horizons made one thing very clear. Even the worlds of the Kuiper Belt, once thought of as frozen, simple leftovers, can be unexpectedly intricate. From Arakoth's softly merged lobes, recording the gentle birth of planetesimals, to Pluto's churning nitrogen glaciers and possible hidden seas, these distant objects hold stories about how our solar system assembled itself, and how ice and rock can dance together over billions of years in the outer dark. Pluto wasn't the only world in that distant system to step out of the blur. When New Horizons swept past, its cameras also turned toward Charon, Pluto's largest moon, and the views were as quietly startling as anything seen on the dwarf planet itself. Charon's surface is crossed by a dark, winding belt of cliffs and chasms near its equator, a tectonic scar that wraps much of the way around the moon, like a great split frozen in mid-stretch. That vast system of canyons hints at a story deep inside. One picture many scientists favor is that Charon once held an internal ocean of liquid water mixed with antifreezes such as ammonia, warmed by the leftover heat of its formation and by the tug of war between Pluto's gravity and its own. As that ocean slowly cooled and froze, the ice would have expanded. With nowhere else to go, it pushed outward on the crust, cracking and lifting it until the surface tore open into long fractures and fault-bounded blocks. The equatorial belt we see today may be the fossil record of an ocean that has long since turned to solid ice. its restless days remembered only in the shape of the rocks above. Scenes like this, Charon's cliffs, Pluto's heart-shaped glacier, Arrokoth's softly fused lobes, are little windows into larger questions. Every crater, every ridge, every unexpectedly smooth plain offers another clue about how small, icy worlds behave over billions of years, and how the building blocks of planets once came together. New Horizons is still coasting through the Kuiper Belt as a silent witness to that ancient debris field, riding the outward tail of its trajectory. Sometime in the late 2022s, around 2028 or 2029, it will drift past the region astronomers usually define as the outer edge of the Kuiper Belt. Mission teams are still watching for any new object that might lie close enough to its path for another close flyby. The sky is wide and the targets are faint, but it is possible that one more small world will wander into reach. Even without that, the spacecraft keeps making distant measurements of dust and charged particles, tasting the environment of the outer solar system as it goes. Each bit of data helps sketch in the texture of space out there. How much dust is floating in the dark, how the solar wind thins with distance, how the sun's magnetic influence slowly unwinds. Closer to home, new eyes have turned toward Kuiper Belt objects from afar. The James Webb Space Telescope, sitting in cold darkness far from Earth's glow, is sensitive enough to pull faint spectra from some of these remote bodies. By studying the colors of the light they reflect and emit, astronomers can tease out hints about their surfaces, which ices coat them, whether complex organics stain their crusts, how radiation has altered their skins. Each dataset is like holding up a tiny, icy shard from the early solar system and turning it under a lamp, looking for subtle tints that reveal what it is made of and how long it has been exposed. In time, our tools may reach farther still. A future mission might not simply race past a Kuiper Belt object, but slow down and enter orbit, mapping it over months or years from every angle. Another could carry a lander to touch down on a surface as cold and dark as a deep winter midnight, scooping up grains of ancient ice to examine on the spot, or even sealing some of them away for a slow journey back to Earth. It is easy to imagine a small robot sitting in the weak sunlight, instruments humming gently, surrounded by a sky in which the sun is only a bright star and the Milky Way is a crisp river of light. However far we go, there is always a wider boundary waiting. At the edge of the Kuiper Belt, the population of known objects thins, but the sun's pull does not simply stop. Gravity reaches much farther, and theory points to something even grander, surrounding everything you've heard about so far. A far-flung cloud of icy bodies that marks the outermost reaches of the solar system's family. This region is called the Oort cloud. Unlike the flat, ring-like belts closer in, the Oort cloud is imagined as a roughly spherical shell, a dim and distant swarm of frozen chunks circling the sun from all directions. It is so remote that even our most powerful telescopes cannot see its individual members. If you could stand on one of those icy mountains out there, though stand might mean balancing on a gentle slope in almost non-existent gravity, the sun would be just another point of light, barely brighter than the stars around it. Day and night would lose their meaning. Everything would be night, with a single, pale star slowly shifting as you orbited around it over millions of years. Even if we cannot photograph the Oort cloud directly, there are strong hints that it exists. The main clues arrive in the form of long-period comets, fragile, icy bodies that sweep through the inner solar system on orbits that can take tens of thousands or even millions. of years to complete a single loop. Unlike the short-period comets linked to the Kuiper belt, these visitors appear from almost any direction in the sky. Their paths are tilted at all kinds of angles, as if they are raining in from a three-dimensional halo rather than a flat ring. Midway through the 20th century, an astronomer named Jan Oort examined the orbits of these long-period comets and noticed patterns that were hard to explain if they came from interstellar space or from the region of the known belts. Oort himself was already deeply familiar with galactic structure and dark matter. He had spent years studying how stars move in the Milky Way. That experience made him especially sensitive to oddities in orbital data. When he turned his attention to comets, he saw that their shapes and speeds did not match what you would expect if they were simply wandering in from random directions in the galaxy. He found that, when you calculate the farthest point in their orbits, the place where each comet turns back toward the Sun, many of them reach similar distances, clustered in a broad band rather than scattered randomly. No one line is perfect. There is a spread. But the way those aphelia group together suggests that something about their origin is shared. Those most distant turning points lie around 50,000 times farther from the Sun than Earth's orbit. At that scale, even our usual yardstick for space, the astronomical unit, starts to feel small. Neptune, the outermost major planet, circles at about 30 astronomical units. The main Kuiper belt extends from roughly that distance to around 50 astronomical units. A more extended region of scattered objects may stretch to almost 1,000 astronomical units. The long-period comets Oort studied, by contrast, seem to come from a shell whose inner reaches begin tens of thousands of astronomical units away and whose outer edge may blur into the depths of interstellar space. The fact that these comets share similar maximum distances and that they approach from every direction suggests that they are not random drifters from the galaxy at large. Instead, they behave like members of a distant, bound population objects that still orbit the Sun, but on paths so huge and slow that a single circuit can outlast entire geological eras on Earth. Imagine an orbit so elongated that while one end dips past the planets, the other reaches into a region where the Sun is almost lost among the stars. To explain this, Oort proposed that the solar system is surrounded by that great, unseen cloud of icy bodies. Later work refined the picture, splitting the Oort cloud into an inner, somewhat more disk-like region and an outer, more nearly spherical shell. Together, they would contain billions or even trillions of icy planetesimals, leftovers from the time when the planets were still forming, tossed outward long ago by gravitational encounters with the young giants. In the early solar system, after the main planets had taken most of the available mass, much smaller bodies, planetesimals, still swarmed among them. As those planets shifted and interacted, they scattered many of these leftovers. Some were thrown inward and destroyed in collisions with the Sun or planets. Some were ejected entirely, flung into interstellar space to wander between the stars. And some ended up on long, stretched orbits that kept them bound to the Sun, but carried them far beyond the planet region, into the darkness where the Oort cloud now resides. Those distant, slow-moving bodies were not left entirely alone. Even out there, they felt small, persistent tugs from beyond the solar system. Passing stars, giant molecular clouds, and the overall gravitational field of the Milky Way all exerted gentle but cumulative pulls. Over time, these influences puffed up the distribution of orbits, smearing what might once have been a loose outer disk of icy bodies into a vast, nearly spherical cloud. Each encounter is almost imperceptible on its own, but across billions of years, the effects add up, like countless tiny nudges that eventually change the course of a life. In that picture, the Oort cloud is both a graveyard and a nursery, a place where ancient planet-building scraps have been parked for billions of years, and a reservoir from which new long-period comets are occasionally sent inward. A slight disturbance, a star gliding past at a few light-years distance, or the slow tidal pull of the galaxy can shift a cloud object's orbit just enough that it begins a long, slow fall toward the Sunday. For ages, it moves almost invisibly, creeping inward through regions no telescope watches. Only when it reaches the inner solar system do its ices start to vaporize and its tail begin to bloom. Many such bodies will still miss the inner planets entirely, looping silently back outward after their brief, warm passage. A few pass close enough that their ices awaken fully, unfurling tails that make them visible in our skies. From our perspective on Earth, the story seems to begin when a new, long-tailed comet appears low on the horizon before dawn or after sunset. In reality, that bright apparition is only the last page of a chapter that began in the deep quiet at the edge of the sun's reach. Even nearby stars can, from time to time, brush the edge of this remote cloud. Roughly 70,000 years ago, long before cities or written stories, a small star system known as Schultz star passed within a fraction of a light year of the sun, likely grazing the outermost parts of the Oort cloud. From Earth's surface, there would have been nothing dramatic to see, just an extra faint star in the night that our ancestors might not have noticed at all. But on the scale of those slow, cold orbits, such a passage is enough to shuffle trajectories and nudge some sleeping comets onto new, more elliptical paths. When we watch a rare, long-period comet appear in the sky today, brightening night after night as it approaches the sun, we are seeing the end of a journey that may have begun with such a distant nudge. The glowing tail is just the final flourish of a story that started in the quiet outskirts of the Oort cloud, where an icy fragment spent eons circling in darkness before being sent inward for its brief moment of light. And when it fades again into the outer dark, another will eventually take its place, a reminder that even at the farthest edges of the solar system, the story of falling ice and slow orbits is still unfolding, cycle after gentle cycle, in the background of our night sky. Schultz's star, the one that brushed past the far edge of our system some 70,000 years ago, turned out to be more of a quiet passerby than a wrecking ball. It's a low-mass binary, a small red dwarf with a brown dwarf companion, faint and light compared with our Sunday. Even when that pair came much nearer to the outermost icy shells than any star we know of in recent times, their combined gravity was still far weaker than the sun's hold on its distant family of objects. For almost everything in the far dark, the visit passed like a slow, distant wave. If you could have watched from one of those frozen bodies, the star would simply have brightened a little in your sky for a while, then faded again, leaving your slow, elongated orbit almost unchanged. Numerical experiments run on supercomputers suggest that a few members of the cloud probably did feel the tug. Some orbits were likely nudged just enough to become a little more elongated, sending a handful of bodies on paths that, after a very long time, would carry them inward as new long-period comets. But across the whole Oort cloud, the disturbance was gentle, not catastrophic. The sun has been circling the center of the Milky Way for more than 4 billion years, weaving in and out of different neighborhoods of stars, and in that time, there must have been many such flybys. Some stars would have passed a bit closer, some a bit farther, each adding its own faint signature to the cloud's slow evolution. If passing stars routinely tore the cloud apart, it could never have formed or survived. Our best models say the opposite, that while close encounters can shuffle the deck and occasionally swap a few icy fragments between neighboring systems, the cloud as a whole is resilient. Those same simulations hint that Oort clouds may not be unique to us. Other stars, especially those born in clusters where their early environments were crowded, could have their own distant swarms of planetesimals, scattered and puffed up over time into halos of ancient ice. In that light, our Oort cloud is part of a larger pattern, a common end state for planetary leftovers, waiting in the shadows of countless stars. If you imagine flying far away and looking back at the galaxy from the outside, you could picture almost every star wrapped in its own invisible sphere of cold debris, like tiny lanterns, each with a faint, frozen mist you cannot quite see. The picture that emerges for our own cloud is layered. The innermost region, according to many models, may be somewhat more flattened and disk-like, shaped by the same overall rotation that flattened the early solar system's original gas and dust. Beyond that inner zone, the distribution smooths out into something more nearly spherical, a great shell surrounding the sun from all directions. Together, these regions form what we simply call the Oort cloud. Its inner boundary might begin a couple of thousand astronomical units from the sun. Its outer edge may reach 50,000, 80,000, perhaps even 100,000 astronomical units away, shading gradually into the space between the stars. Somewhere in that vast thickness, the sun's gravity and the galaxy's pull are in delicate balance, and small pushes can send bodies one way or the other, either inward toward the planets or outward into true interstellar drift. If you translate that into more familiar language, the Oort cloud could extend for more than a light and a half across, a ghostly sphere of influence wrapped around the tiny bright system we usually draw in textbooks. Distances like that can be hard to feel, so it helps to anchor them with something we've actually built and launched: Voyager 2. Voyager 2 left Earth in 1977, when computers filled rooms and the outer planets were still mostly cartoons in our imaginations. Since then, it has flown past Jupiter, Saturn, Uranus, and Neptune, taking family portraits as it went. Decade after decade, it has kept moving outward. Today, it is more than 100 astronomical units from the sun. Over 100 times farther away than Earth is cruising through the thin boundary zone, where the sun's influence fades and the interstellar medium begins. Its speed is astonishing by everyday standards, tens of thousands of kilometers per hour, crossing several astronomical units each year. If a car moved that fast, it could go around Earth's equator in minutes. And yet, from the Oort cloud's perspective, Voyager 2 has barely left the doorstep. At its current pace, it would take on the order of 3 more centuries just to reach the cloud's innermost regions, and tens of thousands of years to travel all the way through to the far side. That's for one of the fastest spacecraft we have ever launched, already beyond the heliosphere where the sun's charged particles yield to the thin breath of interstellar space. Our nearest stellar neighbor, Proxima Centauri, lies more than 4 light-years away, far beyond even the outer edge of the Oort cloud. When we talk about interstellar or intergalactic travel, these are the scales we are facing. Journeys so long that human lifetimes are thin slices in the timelines involved. More like single heartbeats in a story that spans many ages. Given how distant and dim this cloud must be, it isn't surprising that some people ask whether it really exists at all. After all, we can't point a telescope at it and see a glittering ring the way we can with Saturn's icy debris, or photograph its members the way we image Kuiper Belt objects. Some have suggested that maybe many long-period comets come instead from interstellar space, random visitors falling past the sun for the first and only time, with no home reservoir at all. We do know that such interstellar visitors exist. In 2019, an amateur astronomer named Gennady Borisov spotted a comet whose orbit didn't loop back toward the sun at all, but traced a hyperbolic path, one that would carry it in, around, and out of the solar system forever. Follow-up observations showed that this comet, later named Borisov, carried an unusually high amount of carbon monoxide, compared with many comets thought to be native to our own system. Its composition hinted that it likely formed around a red dwarf star under conditions different from those in our sun's planetary nursery. Before Borisov, astronomers had already identified an interstellar object that did not even carry a visible coma, a shard of rock or ice, passing through on a similar one-time trajectory. Together, they showed that fragments from other systems do occasionally thread their way through ours. Comet Borisov is a beautiful confirmation that chunks of ice and rock can and do travel between star systems. But when astronomers look at the entire population of long-period comets we've observed, most of them behave as if they are bound to the Sunday. Their orbits, when carefully reconstructed, point to aphelia at those tens of thousands of astronomical units we talked about earlier, not to truly infinite, open-ended paths. Statistically and dynamically, a distant, bound reservoir fits the data far better than a random drizzle of interstellar wanderers. The few known interstellar comets are the exceptions that prove the rule. Tiny numbers compared with the steady background of comets whose paths tie them to a very distant, shared origin. So the Oort cloud remains the leading explanation, a structure we have not seen directly, but can infer from the way its fragments occasionally reveal themselves as comets. That raises a natural question. If it's really there, why can't we just look at it? The answer lies in a combination of distance, size, and light. A typical Oort cloud body might be comparable, in scale, to a large mountain on Earth, something like the height of Everest, just a handful of kilometers across. Now place that object thousands of astronomical units away, tens of trillions of kilometers from the Sunday. From such a distance, even if its surface reflects sunlight, the light spreads out enormously before it reaches us. By the time it arrives at Earth, the faint trickle is drowned out by nearer sources and the glow of the sky. Stars and galaxies are visible because they generate their own light, or in the case of galaxies, gather the light of billions of stars together. Planets shine by reflected sunlight, but they are relatively close to the sun, and so receive and return enough light for our telescopes to collect. The asteroid belt and the Kuiper belt, while much farther out than Earth, are still close enough that their brighter members can be imaged with long exposures and sensitive detectors. The Oort cloud lies beyond even the region bathed strongly in the solar wind, in a realm where the sun's light is a distant lantern. Its tiny, icy members simply do not reflect enough photons toward us to be picked up as individual points. In principle, if we had impossibly large telescopes and fantastically sensitive cameras, we might be able to detect a collective glow, a faint, diffuse band of reflected sunlight from all those icy bodies combined. In practice, that glow would be spread across such a huge area of sky and would be so incredibly faint that it is lost in the background. Our instruments are good, but not that good, not yet. Even spacecraft wandering outward like Voyager can only sample the local environment around them, measuring particles and fields. They cannot suddenly turn and image the entire cloud in one sweeping picture. So for now, the Oort cloud lives mostly in our equations and in the pattern of comet orbits plotted on astronomers' screens. And yet this isn't the first time humans have had to trust indirect evidence when thinking about the structure of the cosmos. Long before anyone could watch the Earth from space, careful observers noticed that the motions of the planets were easier to explain if the sun sat at the center of their paths rather than the Earth. Copernicus, and later Galileo, argued for a heliocentric system not because they could see our globe hanging in space, but because the data, the way planets looped and brightened and dimmed, made more sense that way. Their view was controversial at the time, but over the centuries the evidence accumulated, and what was once a bold hypothesis became an everyday fact. Something similar may be happening with the Oort cloud. No single comet orbit proves it on its own, but taken together, the patterns we see, the distribution of long-period comet paths, and the success of models that include a distant cloud all line up in its favor. When astronomers run simulations of the solar system's history with an Oort cloud included, they reproduce the statistics of comets we actually observe far better than simulations without one. One of the quiet joys of science is living in that space between certainty and mystery, where you have enough information to sketch a picture, but not so much that all the questions are closed. The farther we go in time and technology, the sharper that picture may become. Perhaps future instruments will find new ways to sense the farthest icy bodies around our sun, or perhaps a distant spacecraft, launched by people not yet born, will one day send back data from within the cloud itself, listening to the feeble pull of the sun and the hush of the interstellar medium all around. It's also possible that our current understanding will be revised, that we'll discover some new mechanism that helps feed long-period comets into the inner solar system, or find that the cloud has a different shape and extent than we now think. That too would be a kind of success, a better story built on more complete evidence. Science is comfortable with that kind of change. It expects it. Each new idea is a draft that can be refined when more information arrives. Until then, the Oort cloud remains one of astronomy's most captivating enigmas. A vast, unseen population of ancient fragments drifting in the dark, sending us the occasional shimmering messenger in the form of a comet's tail. When one of those visitors appears in your sky someday, perhaps low in the west after sunset or high before dawn, you might remember that its journey began in a place we have never seen, at a distance we can barely imagine. Long before any human eyes ever looked up, closer in, between the planets, and even alongside them, countless smaller bodies share the sun's light with us. There are literally millions of asteroids moving through our system, each with its own path and history, some in familiar belts, others in more surprising places, weaving their quieter stories into the broader tale of how our cosmic neighborhood came to be. Asteroids are some of the quieter residents of the inner solar system. In simple terms, an asteroid is a small body orbiting the sun that is mostly rock or metal, and, on the surface at least, is calm. It doesn't steadily breathe out gas, it doesn't carry a glowing halo, and it doesn't trail a bright tail. Astronomers sometimes call them minor planets, small worlds that never quite grew large. Comets are their more dramatic cousins. They carry ices and other easily vaporized materials close to the surface. When they wander inward and feel the sun's warmth, those ices begin to sublimate, turning straight from solid to gas. The escaping gas drags dust with it, forming a fuzzy coma and, eventually, the delicate tails that can stretch across millions of kilometers of space. Under all that, the central nucleus is often only a few kilometers across, not so different in size from many asteroids. On paper, the old rule sounded simple. Asteroids are rocky and inactive. Comets are icy and active. But out in space, the lines blur. Activity depends strongly on distance from the Sunday. A body sitting far beyond Neptune may stay completely inert for billions of years, its ices locked in the deep cold. Put that same object onto a new orbit that dives toward the Sun, and suddenly it behaves like a comet, venting gas and dust. Likewise, some objects we've long called asteroids may hide pockets of volatiles beneath their surfaces, waking briefly when heated by an impact or a close pass. For this quiet wander, imagine the inner solar system as everything from the Sun outward to Jupiter's orbit. Within this space live most of the asteroids we've cataloged, in the main belt between Mars and Jupiter, and in families that cross the paths of planets. They range in size from dust motes to mountain-sized boulders and up to bodies hundreds of kilometers across. Astronomers don't only classify asteroids by size or orbit, they also look at the color of the sunlight these bodies reflect. Dark, carbon-rich objects belong to the C group. Brighter, stony bodies are the S types, made mostly of rocky silicates. Then there are the M types, where the spectrum hints at a metallic nature, suggesting iron and nickel in large amounts. There are more subtle subgroups as well, but most asteroids can be thought of as variations on those three themes: dark and carbon-rich, bright and rocky, or dense and metallic. Within that broad family, a few stand out not because they are the biggest, but because their orbits or surfaces tell especially striking stories. They're like characters in a quiet novel. The wanderer that almost reaches the edge of the sun's influence, the near misser that once worried us, and the tiny, gravelly world that let a small robot gently touch it and bring dust home. One such wanderer is an object with a dry catalog name, 2005 VX3. On paper, it's about 7 kilometers across, roughly the size of a small city, and easy to overlook among millions of others. But its path is anything but ordinary. At its closest to the Sun, it comes in to about 4.1 astronomical units, a little inside the orbit of Jupiter. From there, instead of looping around on a compact ellipse, it sails outward on an enormously stretched orbit. At its farthest, 2005 VX3 is thought to reach a distance of around 3,000 astronomical units from the Sun, 3,000 times the Earth-Sun distance. Deep into the realm where the Sun is just another bright star. Its orbit is so elongated that astronomers say it has extreme eccentricity, closer in form to a long, thin needle than to the gentle ovals traced by most planets. It spends only a small fraction of its time near the inner solar system, where we can spot it. The rest of its long journey is spent gliding through the dark. The last time it passed through its closest point to the Sun was in early 2006. For a brief season, telescopes were able to track its motion and measure its brightness. Then it slipped away again, dimming as it climbed back out toward the deep. If estimates are right, it will not return to that inner region for another 30 to 40,000 years. Because of its long orbit and remote aphelion, 2005 VX3 may not be a typical asteroid at all, but a dormant comet. an object that once came closer to the Sun on a warmer path and lost much of its easily vaporized ice in earlier passages. After many such journeys, the active ices can be depleted, leaving behind a darker, more rocky shell that no longer grows a bright tail, even when it wanders inward. To our instruments, it now looks like a quiet asteroid, though its deeper history may be closer to that of a comet. From that distant traveler, it's a big shift inward to a world that will pass remarkably close to home in our own lifetimes. The near-Earth asteroid 99942 Apophis. This one is much smaller than 2005 VX3, only a few hundred meters across, but for a short while, it sat at the center of many late-night conversations. When astronomers first calculated its orbit in 2004, using only early tracks, the numbers suggested a small but noticeable chance, about 2.7%, that Apophis might collide with Earth in April of 2029. Initial orbital calculations are like sketching a path while you're still looking through a fogged window. With only a little data, the uncertainty is large, and the possible future positions of the object spread out in a cloud. As more observations come in, that cloud shrinks around the true path. In Apophis's case, the early estimates were worrisome enough that it was given a relatively high rating on the Torino scale, a simple, color-coded system used to communicate impact risk. As telescopes continued to watch Apophis and older images were folded into the analysis, its orbit came into sharper focus. The updated path showed that in 2029, it will pass very close, closer than some of our communication satellites, but will not hit Earth. For a while, a smaller concern lingered: the possibility that during this flyby, Earth's gravity could tweak Apophis's orbit just enough to send it through what's called a gravitational keyhole. A keyhole is a tiny region of space, sometimes only hundreds of meters wide, where a passing asteroid would receive exactly the right gravitational nudge to line it up for a later collision on a future orbit. In the case of Apophis, that future date would have been 7 years later, in 2036. For some time, the chance of slipping through that keyhole kept the asteroid on the lower rungs of concern. But as measurements improved, even that possibility was essentially ruled out. Today, Apophis is expected to be a spectacular but harmless visitor in 2029, a fast-moving point of light sweeping across the sky. If it ever had hit Earth, its impact would have released an enormous amount of energy, on the order of hundreds of megatons of TNT, many times more powerful than any human-made explosion. That's enough to devastate a region, flattening forests and cities across hundreds of kilometers. The fact that asteroids roughly the size of Apophis are expected, from statistical studies, to hit Earth only every tens of thousands of years is some comfort, but also a reminder of why careful tracking and gentle, preventative planning matter. Apophis belongs to the S-type family. Its reflected light suggests a stony composition, built mostly of silicate rock. The most recent estimates put it at roughly 325 meters across, elongated rather than perfectly round. You can think of it as a mountain lifted into space and set tumbling slowly around the Sunday. When it rushes through our sky in 2029, it will be that mountain you're glimpsing, reduced to a pinpoint by distance. From this near-miss story, we can drift outward again, this time to a much smaller body that allowed a spacecraft to come close in a very different way. The asteroid 25143 Itokawa is a Mars-crossing object which means its orbit carries it inside Mars's path at some points and farther out at others. It is tiny on a cosmic scale, only about 500 meters long from end to end, more like a large hill than a world. Yet it became the focus of a daring mission by the Japanese Space Agency, one whose goal was not only to visit, but to touch, collect, and return material back to Earth. Itokawa is also an S-type asteroid, its spectrum matching stony compositions similar to some meteorites found on Earth. Images from the Hayabusa spacecraft revealed a crooked, peanut-like shape, as if two unequal pebbles had been pressed together. This has led scientists to describe it as a possible contact binary. Perhaps once, two separate asteroids that drifted together so gently they did not shatter, but instead merged into a single, loosely held structure. What stands out most about Itokawa is its surface. Rather than being covered in neat, bowl-shaped craters, it appears to be a jumble of boulders, gravel, and dust. The mission team described it as a giant rubble pile, a collection of fragments held together mostly by its own weak gravity. Measurements of Itokawa's mass and volume suggest an average density of about 1.8 grams per cubic centimeter, much lower than solid rock. That number hints at large, empty spaces hidden within, voids between chunks of material, making the asteroid a kind of three-dimensional collage. It is as if some larger parent body was smashed long ago, and the leftover pieces slowly fell back together, forming this fragile, lumpy remnant. Because Itokawa is so small, its gravity is incredibly feeble. A person standing on its surface could jump and, with only a modest push, escape into space. For the Hayabusa spacecraft, that meant it couldn't simply go into orbit the way probes do around larger worlds. Instead, controllers arranged for the spacecraft to travel alongside the asteroid, matching its path around the Sun so that, from Itokawa's point of view, the probe hovered nearby like a careful companion. From that station-keeping position, Hayabusa made slow descents toward the surface. The goal was to briefly touch down, stir up a little material, and capture grains of dust and tiny pebbles to bring home. Despite technical challenges, the mission succeeded. In 2010, a return capsule streaked back through Earth's atmosphere and landed in the Australian outback, carrying precious specks from Itokawa's surface. Those grains, examined under microscopes in quiet laboratories, have helped connect S-type asteroids firmly with a particular class of meteorites, tying what we see falling from the sky to specific kinds of bodies in space. They also offer a tangible link to a place that, for most of us, will always remain out of reach, a tiny piece of a rubble pile that circles the Sun between Earth and Jupiter. Out in the main belt, circling the Sun between Mars and Jupiter, there is a dark world that rarely draws attention from casual skywatchers, but quietly carries a significant share of the belt's mass. This is Pallas, one of the earliest asteroids to be found, discovered not long after Ceres at the dawn of the 19th century. Astronomers who were trying to relocate Ceres after its first sighting, instead, stumbled on a second moving point of light, wandering against the fixed stars in almost the same patch of sky. For a while, Pallas joined Ceres and a few others in the company of planets on the charts of the time, before the growing crowd of similar discoveries forced a new category into existence. Pallas is large enough to command respect among its neighbors. Its diameter is a little over 500 kilometers, slightly greater than that of Vesta, and it contributes several percent of the entire asteroid belt's mass by itself. Yet, it is surprisingly hard to see. Unlike bright, reflective Vesta, Pallas belongs to the dark C-type family, Its surface is coated in carbon-rich material that swallows most of the sunlight that reaches it, reflecting only a few percent back into space, about as dark as fresh asphalt. Even at its best, it is a binocular object, never quite stepping up to naked eye visibility for most observers. Its path around the sun is steeply tilted, inclined by more than 30 degrees to the plane in which most planets travel. That means Pallas spends much of its time sailing above or below the main traffic lane of the solar system, tracing a solitary route through space. For a spacecraft launched from Earth, that tilt makes it a difficult target. To visit Pallas up close, a probe would have to change its own inclination dramatically, spending a tremendous amount of energy just to climb or dive to Pallas's orbital plane. For now, we know it mainly from the subtle clues in its spectrum and from blurred images that hint at a rugged, irregular surface. Farther out, in the region shared by the giant planets, another small body carries a secret that looks, at first glance, like a miniature echo of Saturn. This object, called Chariklo, does not live in the main belt at all, but in the neighborhood between Saturn and Uranus. There, among the cold giants, it moves on a path that marks it as a centaur, a class of bodies that are a little like asteroids and a little like comets, orbiting in the realm of the outer planets. Chariklo is only a few hundred kilometers across, but around this modest body something astonishing was found: a pair of thin rings. These rings, only a few kilometers wide and separated by a narrow gap, circle Chariklo like delicate bracelets. They were discovered not through direct imaging, but when the asteroid passed in front of a distant star. For a brief moment, the star's light dimmed, not once, but several times, as both the main body and the narrow rings blocked it in turn. The pattern of those flickers revealed the ring's presence and size. Chariklo is, as far as we know, the smallest object in the solar system to host a ring system, and the rings themselves should be unstable over long periods at such a small scale. For them to persist, something must be tending them. They may be shepherded by tiny moons, whose gravity corrals the ring particles into narrow bands, in the same way that small moons keep some of Saturn's rings sharply defined. Or perhaps the rings are temporary, destined to spread out and fade over a few million years, a transient adornment that we happen to be witnessing at just the right time. Back in the main belt, another asteroid tells a different kind of story about what lies beneath a surface. Lutetia, a roughly 100-kilometer wide body, is classified as an M-type asteroid, one of the metallic group. Its average density is high, suggesting a large fraction of metal mixed into its interior. Yet when a spacecraft flew past and photographed it, the surface did not shine like bare metal. Instead, it looked more like a dark, dusty, carbon-rich world, its color more reminiscent of the C-type family than of a gleaming iron core. One way to reconcile these clues is to imagine Lutetia as a metal-rich body wrapped in a thick blanket of rubble. Over billions of years, impacts may have ground the upper layers into a layer of loose material called regolith, several kilometers deep in places. Craters on Lutetia's surface often have softened rims and muted profiles, as if they have been partly filled and smoothed by sliding dust. Beneath that cloak, the asteroid's core may be more solid and metallic, the remnant of a once hotter, partially differentiated body that never grew large enough to become a planet, yet still carries a trace of that internal segregation of rock and metal. From massive, dark Pallas and buried metal Lutetia, we can drift in our thoughts to a smaller, more immediate neighbor, Eros. This elongated, peanut-shaped S-type asteroid is about 30-odd kilometers long and orbits mostly between Earth and Mars, sometimes coming close enough to qualify as a near-Earth object. It was the first asteroid ever found with an orbit that carries it inside Mars's path, and its trajectory is not stable forever. Over spans of tens or hundreds of millions of years, gravitational nudges from planets will slowly reshape its orbit, and there is a real chance that one day it will evolve into an Earth-crossing body capable of colliding with our planet. Eros has already received a visitor. At the turn of the millennium, NASA's Near-Shoemaker spacecraft slid into orbit around it, mapping its surface in detail. The images returned showed a landscape of ridges, grooves, and craters, but also smooth swaths where fine material had pooled, as though the asteroid's weak gravity had allowed dust to sift downhill into low places after each impact. The mission ended with something that had not originally been planned. Controllers gently guided the spacecraft down to the surface itself, turning an orbiter into an impromptu lander. Like Itokawa, Eros is a rubble-rich world, but on a larger scale. Studies based on NIRS data have suggested that within its volume lie enormous quantities of metals such as nickel, gold, and platinum locked into its rocky matrix. Numbers are only estimates, but they run into billions of tons, enough to make any economist's head spin, even though actually extracting and transporting such material is still far beyond our current reach. For now, Eros remains a reminder that the inner solar system's small bodies are not just relics, but also potential resources, carrying in their bulk the heavy elements that were forged in ancient stars. Another asteroid in the belt, Ida, adds companionship to the mix. When the Galileo spacecraft was on its long journey to Jupiter, mission planners arranged for it to pass near 2 asteroids along the way. The second of these, 243 Ida, revealed a surprise. Ida itself is about 30 kilometers long, an irregular, dog-bone-shaped S-type body with a heavily cratered surface that speaks of a long, battered history. But orbiting this modest world was an even smaller one, a tiny moon, later named Dactyl. Dactyl is only about 1.5 kilometers across, a miniature companion circling a miniature primary. The discovery was more than a curiosity. It provided a rare chance to measure Ida's mass and density by watching Dactyl's orbit, and it confirmed that even small asteroids can host natural satellites. Many such asteroid moons are known now from radar studies and other spacecraft flybys, but Ida and Dactyl hold a special place as the pair we have actually seen together in detailed images. From Ida's tiny moon, we can let our thoughts return to a much grander survivor in the belt, one we have already brushed against earlier, Vesta. Among the asteroids, Vesta is something like an unfinished planet, with an interior that once separated into layers, dense core, rocky mantle, and crust before its growth was stunted. Its southern hemisphere bears the scars of titanic impacts that carved out huge basins and launched fragments into space. Some of those fragments eventually fell on Earth as meteorites, allowing us to study pieces of Vesta's crust and mantle in our hands. The Dawn spacecraft's time around Vesta revealed towering central peaks, deep troughs girdling its equator, and the complex structure of those southern basins. In its early days, that central peak in the Rhea Silvia Basin was thought to be the tallest mountain in the solar system. Later measurements returned the official record to Mars's Olympus Mons. But Vesta's peak remains a staggering structure when you remember how small the body that hosts it is. On a world only a few hundred kilometers across, A mountain tens of kilometers high rises almost like a spike, a frozen monument to past violence. Vesta's membership in its own spectral family, the V-type asteroids, and the match between those asteroids and the HED meteorites found on Earth, have made it a kind of Rosetta Stone for understanding how rocky bodies heated and evolved in the young solar system. It stands midway between the simpler, undifferentiated rubble piles and the fully formed rocky planets, a fossil of a stage most planetesimals passed through and then left behind. And then there is Ceres, the quiet giant of the belt, larger than any other asteroid and massive enough to be rounded by its own gravity. Ceres occupies a special category, a dwarf planet sitting amidst much smaller neighbors. Its diameter is close to 1,000 kilometers, and it holds roughly a third of the entire asteroid belt's mass inside its muted globe. For a long time, it was just a bright dot in our telescopes, then a fuzzy disk. Only when dawn slipped into orbit around it did its face resolve into craters, plains, and those now famous bright spots that drew so much attention. Ceres appears to be a mixture of rock and ice, with a lower density than purely rocky bodies like Vesta. Models suggest a rocky core wrapped in a mantle rich in water and salts, overlain by a crust of darker, dusty material. In some places, briny water from within seems to have risen toward the surface, leaving deposits of bright, reflective salts when the water sublimated away. These patches gleam against the darker background. One crater in particular, Okator, hosts a cluster of such bright spots on and around a central dome. Observations have hinted at occasional hazes there, suggesting that even today, Ceres may vent tiny amounts of water vapor, an exceedingly gentle form of activity compared with the roaring plumes of larger worlds. But activity all the same. For a body adrift in the asteroid belt, it is a quietly complex place. Ceres, Vesta, Ida, Eros, Lutetia, Chariklo, Pallas, and the many other named and numbered bodies we've touched on are only a few among millions. Yet each one offers a different angle on the story of how our system formed and how it continues to change. Some carry memories of internal oceans now frozen solid. Some show the bruises of repeated collisions. Some hold metals in unexpected abundance. Some wear rings. Some keep tiny moons. If you zoom out in your mind, all of these worlds together form a kind of bridge between dust and planets. They are the pieces that never quite combined, the shards left over from bigger mergers, and the fragments chipped off in later impacts. They drift between orbits, cross paths, and occasionally fall inward, as meteors and meteorites that streak through our skies or end up in our museums and laboratories. Late at night, when the sky is clear and still, you might step outside and look up, knowing that beyond the familiar stars and constellations, countless small worlds are moving in their own slow patterns around the Sunday. Most of them are too faint to ever be seen with human eyes alone. Yet they are there, shaping and being shaped by gravity, sunlight, and time. In their silence, they hold the rough drafts of planets, the leftovers of collisions, and the clues to stories that began long before Earth cooled enough for oceans and life. Thinking of them this way, the solar system feels less like a tidy family of 8 major planets and more like a vast, gently cluttered space. Between and beyond the big worlds, asteroids and comets and dwarf planets keep circling, their paths overlapping and intertwining over spans of time so long that our own lives barely register. They are small, but their stories are not. As we send more patient spacecraft to meet them, hovering beside rubble piles, slipping past ringed centaurs, Orbiting dark protoplanets, we slowly turn those points of light into places, and those distant places into part of our shared map of home.